Yeah, hello everybody. I'm so glad to open up the macOS and the iOS security track here on Nullcon. So my today's talk is broken isolation, draining your credentials from popular macOS password managers. So as I was introduced, I'm Wojciech Regula. I'm head of mobile security at Securing. I have reported over 60 CVs. Yeah. Closer. Okay. Can you hear me now? So maybe I can just grab it. That's gonna be okay. I have now more than 60 CVs registered in Apple, so I always say I spent too much time already on researching Apple stuff. I'm focused on iOS and macOS application security. And somebody of you may know me from certified as iOS application security engineer course. I will talk about this at the end of the talk. And all the things I discover, I usually, after some delay, of course, I blog on my blog, which is wojciechregula.blog. If you don't want to use that long Polish name, just use the alias for this website, which is osx.zip. At the moment of creating that domain name, I didn't know that my first name is non-pronounceable in English. So then a lot of people reported it to me. So I bought another domain, which is osx.zip, which will redirect you to this blog. And I'm iOS Security Suite creator, which is an open source jailbreak detection library made mostly for OWASP application security verification standard compliance. So if you are creating iOS apps and you need to be compliant with OWASP MAS-VS, that's a thing to check out. Okay, so the plan for today's talk is I'm going to start from introducing you to macOS security and isolation mechanisms. And actually, I called this talk a talk with a mission because I think there is a lot of misconceptions about macOS and iOS technologies in general. People tend to compare macOS to Linux, which is not true. And thinking of macOS as it was a Linux will lead to different problems, various vulnerabilities, so I will explain it at the beginning. And when we will be all standing on the same ground, we'll be understanding the foundation of macOS security. We're gonna talk about pawning password managers. And the password managers are selected in that way because they are written in different technologies, or there are different contexts in which they are used. So every password manager listed in here is used in another context. You will see what I mean later. And at the end, because I don't want to leave you without recommendations, especially if there are developers in the audience, you must know how to create your software properly. So I will talk a bit about the recommendations. Great. So let me start from my favorite slide, which is historical slide with the diagram with operating systems. I can see that the resolution is not great. So I will simply tell you what's on the slide. So here we have the Linux evolution. And here you have macOS. And you will see that that's another branch. The macOS has mostly two parents, right? So the first one is FreeBSD, and this is the, let's say, Unix foundation. But you have also the next step foundation, right? So you have two parents. And whenever the BSD, the BSD part is mostly responsible for process management, signal handling, user and group management, syscalls, TCP, IP stack, and sockets, so the Unix things. The Mac part of the microkernel, which is in macOS, is responsible for processor scheduling, multitasking, virtual memory management, inter-process communication, and Mac traps. So even if we take a look at syscalls on macOS, you will see that, okay, we have the typical Unix like syscalls, but we have Mac traps, which can also be compared to syscalls. So we have one operating system, but the kernel is divided, it's, let's say, split into two parts. We have the big monolithic kernel in which we have a microkernel. That's really important thing to understand. So Mac and BSD each maintain different security models. So Mac's security model is based on port rights, wherever the BSD security model operates based on process ownership. That's really important to understand. I will describe it later why it's that important. So we have different operating systems in the Apple world, like macOS, watchOS, visionOS, iOS, tvOS, iPadOS, but you will see that under the hood, the kernel, at least a large part of it, will be the same. And by the way, it's open source. So the kernel extensions will be different, of course, for macOS and iOS, but the kernel itself will be mostly the same. And this is the an old image taken from Apple's documentation on which they implement every operating system having this picture in mind. So we have software and hardware and firmware layers, and you will see that on hardware level we have security enclave, secure element, crypto engine, device keys, etc. So I'm not gonna dive into it because this is not the what this talk is about, but we are interested in this part on software layer. So we have the file system, we have the OS partition, which is, by the way, unencrypted, which is a misconception usually. Like people think that, okay, everything on macOS on iOS is encrypted, but it's not. Like OS partition is sealed. It's cryptographically sealed, but there is no point of encrypting the data, which is, this is just an operating system. There will be a verification if that cannot be changed, right? But itself, the OS partition is encrypted. And you have the user partition, which is actually encrypted. In theory, every application should be put in sandbox, right? Every application you install on your iPhone will be in sandbox. There are daemons on iOS that are not sandbox, but the applications generally are sandbox. The same goes for visionOS, watchOS, iPadOS, etc. But on macOS, putting your application in the sandbox is not mandatory. It's up to the developer if a developer wants to put their application in sandbox or not. And here comes the thing that I call the big hallucination, because actually on macOS, even though the application is not put in the sandbox, so you open up Activity Monitor, you can see if application is sandboxed and not, or it's not. And even if you see that application is not sandboxed, in theory, we are all living in a global hallucination, which is called system integrity protection. And system integrity protection, if it's turned on, it's based on sandbox kernel extension. If you take a look on it from the perspective of security researcher, you will see that system integrity protection actually enforces a global sandbox on every process that's running, right? So even though we think we are not in the sandbox, with standard macOS configuration, we will be in the sandbox. So, to sum up what I said at this moment. So macOS is totally not a Linux. And the biggest assumption in here is that applications running with the same user ID should not be able to control themselves. So that's an opposite like we have on Unix, right? For example, on Linux, if we have the same permissions, like we work on the same user as the application we want to control, we usually are able to control it, right? If an app wants to be controlled by other apps, like for example debuggers, it must be signed with a special entitlement, which is gom get task allow. So our application must deliberately say, I want to be controlled, I want to be debugged. And ptrace, because some of you may ask me, okay, but on macOS you have ptrace, right? So you should be able, like on Linux, control other apps. Yes, there is ptrace on macOS because macOS has the POSIX certification, let's say, right? But the ptrace is not fully implemented. And if you dive into the syscalls on macOS, you will see that, okay, there are, I think, all of the syscalls that are required by POSIX itself, but sometimes they are implemented differently or they are incompletely implemented. So let's talk about macOS security and isolation mechanisms. I'm sorry, because you showed me that I have 40 minutes for this talk, right? Yeah, I have, because you showed me like 10 minutes left. Okay, just to make it clear. So let's say now about macOS security and isolation mechanisms. So why the boundary between the processes running on the same user ID is that important? Why I started this talk from explaining it? Because without such isolation on macOS, which is a normal thing on Linux, but on macOS it's not. Without the same UID isolation, we'll be able, for example, to impersonate private entitlements. And that leads to, for example, bypassing TCC, which is the privacy framework. So the all privacy restrictions on macOS will be gone. With private entitlements, you can impersonate, with the private entitlements, you can impersonate, and if there would not be the same UID isolation, you would be able to ask some daemons to get you root permissions. So there will be no user to root security boundary if you can impersonate private entitlements. There would be also a SIP bypass, because you would be able to assign yourself an entitlement that completely bypasses the SIP. So you'll be out of the matrix of the global hallucination sandbox, I like to call it. Of course, you would be able also to trick third-party XPC services, etc. But the most important thing is that without user ID, the same user ID isolation on macOS, you can do whatever you want. There is no security boundary, almost no security boundary on macOS if there is no user ID separation, which on Linux is a standard stuff, right? On Linux, that's totally okay. So thankfully, Apple documented a lot of security assumptions in the of their platforms in the Apple Platform Security White Paper, which is available online. But unfortunately, not everything is well documented, so we need to do some reverse engineering. So let's start from the system integrity protection that I mentioned. It's based on the sandbox kernel extension, and it will restrict access to many directories on macOS. It will also deny you a debugger to process signed directly by Apple. And system integrity protection is also known as rootless, because even if you have root, you cannot do the above mentioned operations when the system integrity protection is turned on. And when turned off, there is no privacy controls on macOS, and any application may elevate their permission, their privileges from user to root. And there is a funny thing. Whenever I perform a macOS infrastructure audit, the very first thing I do is to verify if all the macOSs have system integrity protection turned on in the infrastructure. This is actually the very first thing I really do, because I saw it too many times. Whenever you try, let's say you have a problem with macOS, right? You're developing something and something doesn't work. So, and you put the question to Google, like, how can I fix that? And you will see that, okay, there are some Stack Overflow answers. So please click on the Stack Overflow answers. You will see really many times that the most voted answer, or the voted answer in top 3 of votes, will have the following answer. Okay, so disable system integrity protection and the application will work fine. That's really like a common thing on Stack Overflow, and many developers do that. But please remember, without system integrity protection, the isolation on your macOS is gone. The privileges, the root doesn't matter. You can probably load your kernel extensions, etc., etc. So whenever you do macOS infrastructure audits, verify if every computer has the system integrity protection turned on. And you can check it with the following comment. It's that easy. CSR util status. Okay, so let's start experimenting with macOS. Let's inject, for example, logdaemon with Apple's debugger with root permissions. So we use Apple's debugger and we have root permissions. And let's choose, for example, logdaemon. You will see that attachment has been failed. So let's open the console app, and you will see that under the hood, the debug server, which is the part of LLDB, was about to run a task for pit function, which actually is a Mac trap. So it's like a syscall, but in the Mac part of the kernel. And you will see that the attachment has failed. Because as I told you, we are not able to control, even we have the same user ID, other applications. So even if we have a root, we used Apple's debugger, that's not gonna happen. So debugging a process, which of course gives you a path to code execution within its context, requires getting the task port of the debuggee. So it involves getting the task for pit function, as I've just showed you. And task for pit is the function or the Mac trap, which is really restricted on macOS. And the task for pit requests are controlled by the taskgate daemon and MFI, which stands for Apple Mobile File Integrity Daemon. So when the system integrity protection, when it's enabled, which is the default configuration, the task port retrieval is not possible when the target app is a platform binary or has a hardened runtime. That's a blob of text, but if you are into macOS security research, take a picture of that or note it somehow, because this is the slide I really wish I saw like 6 years ago. There's an instruction on how you can control other processes. So if the debuggee holds a public com Apple security get task allow entitlement, the injection is possible even by the same user, so there is no root required. So this is the situation when our application says, I want to be debugged, and explicitly includes an entitlement that says, I want to be debugged. If the debuggee doesn't have the hardened runtime and was signed without the get task allow entitlement, the injection is still possible, but you need root permissions for debugging such an application. Of course, if it's not an Apple app, right? The injection is always possible when the debugger app holds a private system task ports entitlement. But for your information, LLDB or any other official debugger doesn't have such an entitlement. Maybe in Apple they have an NLDB version with that entitlement, but of course that's not released to the public because that breaks the isolation, right? So what happens if you want to create an application with a private entitlement? So we have a simple hello world. We added the private TCC manager entitlement. We sign it, and if you want to spawn the application, you will see that, oh, that was killed. And if you open the console log, you will see that, unfortunately, MFI killed the application because there were restricted entitlements. And there is a fun fact. 5 years ago or 6 years ago, I reported to Apple that they include in macOS some debug builds of their some of the daemons with the get task allow set to true, that to the daemons, and the daemons had also the private TCC permissions. So I was able to take over some Apple daemons, execute code in their context, and get access to some TCC restricted sensitive privacy data. That's just for your information. It's a funny twist in this story. Okay, so because this talk should be about password managers, right? The password managers are third-party applications. So if we want to take over password managers, we'll be looking for password managers with get task allow or without the hardened runtime. But what actually is the hardened runtime? So according to Apple, hardened runtime, along with the system integrity protection, protects the runtime integrity of your software by preventing certain classes of exploits like code injections, dynamic linked library hijacking, process memory space tampering. So in short, it blocks code injections. And the thing is that nowadays, all software downloads from the internet must be notarized. That's yet another mechanism. And notarization enforces the hardened runtime to be turned on. So in practice, all the applications you download from the internet should be notarized, right? Because notarized, and because they are notarized, the hardened runtime should be turned on. So hardened runtime should be only in very old applications before the notarization has been enforced. This is a screenshot from Apple's documentation. So it explicitly says that applications must be notarized and the notarization requires hardened runtime. So how does the hardened runtime is enforced? Unfortunately to us, it's enforced by setting a code signing attribute. So it's in the code signing section. So we should not be able to modify that because we'll break the signature if we modify that bit. And if you want to see if an application is has hardened runtime or not, we can use CodeSign tool. It's that simple. However, that's our research is not like stopped by the fact that hardened runtime should be enforced, because there is something called runtime exceptions, which is really nice to us as researchers. And I marked two interesting exceptions in terms of code injections. So the first one is allow build environment variable entitlements, and the second one is disable library validation entitlement. So the first one allows us to set a dynamic library that will be loaded to the process space. However, maybe you know it from Linux, like LD preload. This is the same thing on macOS. However, nowadays, macOS will block loading an untrusted dynamic library if it's not signed by Apple or it has been signed with a different developer certificate. So, if we want to load a library that's untrusted, like if we want to target third-party password managers, it's understandable that our dynamic library is untrusted. We would need to disable the library validation, or we need to find an application that has a hardened runtime exception that allows, for disabled library validation. Great. So how can we check it? So we open CodeSign with ---- entitlements, and in this example, for example, Firefox has the disable library validation turned on. By the way, I reported it to Firefox, I don't know, like 6 years ago or something, and Firefox told me that they need to disable library validation because they need to maintain Flash compatibility. And for some reasons, Flash cannot be signed with the same certificate. So that's a funny thing. Great. So here we have, that's the last slide before we start pawning password managers. If you want to pawn password managers or any third-party applications, that's also a good resource for bug bounty. We will be targeting apps with getTaskAllow without hardened runtime, with hardened runtime, but with some useful runtime exceptions, and applications that have custom debugging feature that don't depend on getTaskAllow. So here, wink, wink, Electro. Great. So let's take a look at the first one, which is MacPass. It's a native macOS KeePass client written in Objective-C. You can download from GitHub. Really nice project. I really like it. But if we check its entitlements, we'll see that, okay, we have hardened runtime set, but we have disabled library validation also. So normally before, like 2 years ago there was no mechanism called app protection. Nowadays, if you put your application to applications directory and you run it, that directory of that application you just drag and drop there will be protected by SIP. So you would not be able to modify its directory. The only thing that can modify without 0-day the directory of the application is the application itself or Apple binaries. Apple binaries with another special entitlement. So, of course, the application with the same team identifier should be able to modify the contents of the directory because, for example, an updater must be able to update the contents of the directory. So that's understandable. But let's say attackers, we should not be able to modify that directory. So the attack scenario when we can just change one of the MacPass dilibs will not work nowadays on modern macOS versions. So we need to understand in general why MacPass disables the library validation. And the answer is really easy, because it wants to be open for plugins. And where are plugins stored? Of course, they are not stored in the application/MacPass because it would break the MacPass's signature. So it loads the plugins from home directory /library application support MacPass, which is by the design, it's not a protected directory. That's the design decision. That's like appdata on Windows, for example. That's the directory which is not protected by anything. So we can abuse this feature to create a malicious plugin that will just try and drain all the entries when user unlocks the vault. And here you have the demo. So we first check if MacPass, what's the identifier of MacPass? Now we can see if the plugins are allowed to be loaded and where is the database location. So now let's change this preference to be able to load the untrusted plugins, so load uncompatible plugins to true. Now let's just copy the plugin. As you can see, we don't use root in here. We are same on the same user privilege level, right? User to user. And in the temporary directory, we just dump the master password, all the entries that a MacPass had. So this is the first exploit. And it works still, by the way. It's because I can even do a quick question to you. So raise your hand if you think that it is a feature of MacPass. Or you raise your hand if you think it's a vulnerability. Usually when I talk about password managers, the answers from the audience is like 50-50. So this always opens up a discussion. The plugin is the malicious plugin is very easy to code. Here you have the whole code. I can even share it with you if you ask me after the talk. But let's focus now on the second password manager, which is Keeper. It's written in Electron and it's distributed via Mac App Store. So, as I told you like 5 minutes ago, all applications downloaded from the internet must be notarized, and notarization enforces hardened runtime, right? But if you take a look at Keeper Password Manager, you will see that flags are none, which means hardened runtime is not enforced. So did I lie to you? And the thing is that because Keeper has been downloaded from Mac App Store, the notarization in Mac App Store doesn't happen, and it's not required. So, does it mean that apps downloaded from the internet are more secure than those downloaded from Mac App Store? Because notarization is the mechanism that verifies apps for malware, etc., and enforces all the hardened runtime stuff. It makes sure that getTaskAllow is not in there. So, in Mac App Store, there is no such a requirement. So I wanted to determine if I just find a 0 day if that's a vulnerability, or if it's a design problem. So I tried to find it in Apple's documentation, and actually in Apple's documentation you will see that you have the sentence, add the hardened runtime capability, which is not necessary for App Store apps, but is best practice for new code. So, okay, if you want to distribute your app outside of Mac App Store, you need to be compliant with all the notarization strict requirement, but for the Mac App Store, it does not even exist. It's a good practice. That's weird. That's weird. But because we don't have hardened runtime enabled, we can just simply load our library into the Keeper. So that's like really easy. I just loaded my keylogger, just for proof of concept reasons. Yeah. And you will see that my keylogger just dumped the master password of Mac Keeper. So we've broken, again, the isolation between processes on the same user ID. The keylogger is really simple. You can find it on my GitHub. I usually release all the stuff I'm showing on the presentation, so it's not confidential. Great. So let's take another password manager used in a different context, because here we'll be downloading NordPass directly from the internet. It's really popular password manager, which is written in Electron. But you will see that some critical Electron fuses are turned on, which again allows us for code injections. Like 2 years ago, I had a talk on DEF CON in Las Vegas, where I released a tool called Electronizer. So if you're interested in pwning Electron applications, I created an open source tool for that. So it's called Electronizer. You can see it in my talk on DEF CON, Electronizing MacOS Privacy, which is online available. So how to see the Electron fuses? Just use npx electron/fuses read and provide the application. And in case of NordPass, you will see that enable node CLI inspect arguments fuse is enabled. So if you see my talk, you will see that gains us ability to get over the application we want to target. So let's use my tool, the Electronizer. Before that, we'll export some environment variables, which will make our exploitation easier. We can also avoid doing that, but that's just a proof of concept, right? We are not writing a commercial spyware or anything like that. And then the Electronizer. So we are not taking over the task port here, right? We abuse a custom debugging feature to take over the process. User provides the password. And you will see that in TMP NordPass password txt, we have our master password dumped. Okay, again, so who thinks this is a feature? Raise your hand. And who thinks this is a vulnerability? Again, exploit really simple. Just a few lines of JavaScript code. Alright, so KeePassXC. Download directly from the internet. Open source. Native, which uses Qt. And very well documented. I really recommend using KeePassXC. I really like the developer's approach in developing that application. But here, we will not be focusing on the main app. We'll be focusing on the browser extension. That's, just to show you another scenario of attacking password managers. And you will see that in their documentation, which is really large, don't even read it. I will short it. There is a asymmetric crypto between the browser extension and the main app. But the browser extension must store the key somewhere, right? Because it must encrypt the information that is being sent to the main app. And the problem is that generally browsers on macOS are not known for the best isolation practices. So we can simply grab the private key from the local storage or logs and spoof the connection with KeePassXC app. It's that simple. So all the crypto that is between the communication can be bypassed. Let me show you the demo. So we have the KeePassXC password manager. We have some entries inside, as you can see. This is the whole code of the exploit. There is even a Python library created to interact with the main app. So the only thing we need is the communication ID, which is that, and the master password, the private key, let's say, right? No, not private, not master password. Master password is for unlocking the vault, but it's a private key. So yeah, we just take the private key, and here we have all the entries. So that easy. We didn't even have to, inject to the password manager. We just spoofed the communication between the browser extension and the main app. Here we have the code. So who thinks this is a vulnerability? And who thinks this is a feature? Oh, we didn't use any we didn't use any exploit. There is no exploitation. We just took the private key, the communication ID, and we just talked by a protocol that is even documented by KeePassXC, right? There's no vulnerability, right? Great. So let's now talk about the last one, which is LastPass, which is a plugin-only password manager. So there is no standalone macOS app, and all the decryption and encryption happens in the browser's JavaScript runtime. So do you remember what I just told you about the isolation practices in browsers on macOS? Yeah, that's the last one. So there is a software called Selenium, which is used mostly by quality assurance engineers to verify if websites have been built properly, etc., if everything works. So we can use Selenium to just control our browser. And because the password manager here, the LastPass, is a browser extension, which is like, let's say, a part of the browser, it runs within the browser's context, and we can control the browser, we don't have anything more to, just drain all the entries. So let me show you the exploitation recording. So the browser has been opened. The vault is being decrypted in the process context. And we dumped an entry, for example, for gmail.com, right? And why this was possible? Because we have been controlling the browser, right? So we don't even care how, in that case, LastPass encrypts all the stuff inside, right? We just ask the browser extension to decrypt its vault, and we just grab all the entries. And the master password in that case is not provided because there's an auto-unlock feature in LastPass. So we don't care about all the crypto. We just ask the browser to get us the entry. Great. So let me sum up with everything. So I started this talk by explaining you how all the isolation mechanisms work on macOS. So now I believe you understand that the same user isolation is really important. Without the same user isolation on macOS, which is different than in Linux, there is no security on macOS. You can cross almost every boundary because you can impersonate some private entitlements, you can be root, you can load kernel extensions, etc. So the isolation is really important. And then I showed you 5 password managers used in different contexts, and I bypassed them all. So I think you can now an understanding how password managers can be attacked by also other third-party applications, so you can use that knowledge in participating, for example, in bug bounty programs. So, recommendations for macOS app developers: enable hardened runtime, review protect exceptions you put on the hardened runtime you just enabled, enable sandboxing, because now TCP protects also containers of sandboxed apps, notarize your apps if that's necessary, but if you distribute them outside of the App Store. If you use Electron, please disable all the problematic Electron features, because if they are enabled, you can just, as I showed you, with Electronizer, you can just spawn that app, and pen test your applications. And at the beginning of this talk, I mentioned my iOS application security engineer course, which is for developers and iOS pen testers. So if you want a discount, please contact me on LinkedIn or on X. However you want. I'll be happy to talk with you. But for this talk, it's all I wanted to share with you for today. Thank you very much. I don't know if you have time for a Q&A.
We can have 2 questions.
Okay.
Guys, any questions?
Oh, that's okay.
Hello. So I come from Windows land, and I had a question to draw parallels to macOS. So in Windows, we have a isolation feature where every program can run in its own Hyper-V space, which is like hypervisor-based separation. So how does Mac implement its user space isolation?
because that's probably easier for recording stuff. Well, so on macOS, the user space isolation happens in some different layers, let's say. The most important thing is that you need system integrity protection to be enabled, right? Because that enforces the isolation. And then, for example, if for the isolation on the injections level, there's SIP, there's taskgate daemon, which is responsible for, retrieving task ports, for example. But then, for example, if you sandbox your application, there is also the sandboxing level, because probably you understand sandbox from Windows or from Linux, that your application, when in sandbox, cannot access resources outside of the sandbox. But on macOS, sandbox works in both ways. So if your application is in the sandbox, there is something called container that is created for that application, and macOS makes sure that other applications will not be able to access that container. To be honest, I don't have enough knowledge about Linux to answer that question, but I think that's Apple's proprietary mechanism, because there will be some, TCC exceptions for accessing that container, so I don't think that will be the same. But if you know the answer, you can answer it. I don't know how is it. I don't know the details on how on Linux it is implemented, but on macOS it's a clearly proprietary mechanism.
Okay, let's have one last question. We have someone from there.
All this seems to be vulnerable features, but
Sorry, I cannot hear. Can you close the door, please?
all this seems to be vulnerable features, but how was your report? I mean, how did they respond to your reports?
Oh, well, I think because I reported some things to more than the list of password managers to which I send reports is larger than on this talk. But I think only 2 or 3 wanted to even fix it. Some responses were like, okay, we don't believe that's a vulnerability because on other operating system that's totally fine that you can control password managers.
What about the Apple one? I mean, how did Apple respond?
Apple's one. You mean the
Library. The first one you told us about.
Once again?
The first one you told us.
Where I was, I don't know.
The library one. How did the Apple respond? Did you send the report to Apple as well?
But you mean to the passwords app, like the Apple's password manager, or if I send information about NordPass, for example, to Apple? I don't understand the question, sorry.
So initially you told us about one vulnerability, which is a feature provided by, so the apps downloaded from App Store.
Yeah. Okay. So ask me if I reported the behavior that Mac App Store does not require notarization.
Yes.
As you can see in the documentation, they claim it's a feature. So I didn't send a report because the documentation specified, right, that there's a best practice for new code, but they claim it's a feature. So I didn't even report it to Apple. But okay. I think Apple already saw this presentation. So if they want to do something with that, they will do.
Thank you.
Okay, guys, let's have a huge round of applause for Mr. Wojciech, or may I say our hacker, Mr. Wojciech.